Alright guys, let's talk today about wormholes. Are they even real?
Is this real?
That's really one of those questions where the answer depends on what we define as a wormhole and what we define as real. We can define something to be real if it's a mathematical reality, right? So like wormholes could be real in the sense that like Einstein's equations allow them. The math could work out where they pop out as possible solutions to general relativity. But if by real we mean that they're physical objects that we've seen in the universe, then we gotta see if it really is possible. Still, if the universe is infinite, the possibility could remain, and the universe is sort of infinite. So maybe they do exist out there waiting to be discovered. The real question is, are they physically possible or just a mathematical curiosity? We'll dive into the math in this video. When I was looking at my YouTube statistics, I found out that only 2% of my viewers are actually subscribed to the channel. So if you enjoy this kind of content, please do subscribe. It's literally free for you to do and it helps me a lot. Thank you, and let's get back to the video. Alright, let's talk about the theory and math. So wormholes come from solutions in Einstein's field equations, which describe how matter and energy curve space-time. One of the particular solutions, which we call the Einstein-Rosen bridge, connects two distant regions of space-time. The basic idea is that space-time isn't flat. It can curve, fold, and in theory connect in shortcuts, and wormholes would be these shortcuts. But by default, these wormholes are not stable. They collapse almost instantly unless something like an exotic matter with negative energy density holds them open. That's where the math gets wild. So let's talk about the math behind why wormholes probably should exist. This equation here is Einstein's general relativity in one line. On the left side here, we have the geometry, how space-time curves, how it's shaped. And on the right side, we have physics, matter, energy, and everything else. Wormholes don't really come out of thin air, obviously. They're possible solutions to this exact equation. It's like the rules of the universe saying, here's the way space-time could bend, and see what you can find from it. Whether nature actually uses this solution is another question, but obviously, Einstein's general relativity has held up for about a century by now, and we don't see any signs of it slowing down. Now, the Schwarzschild black hole metric describes the geometry here around a non-rotating black hole. Time and space are warped by mass. And this metric shows how space-time is shaped around a non-rotating black hole, like I said. Notice that there are two terms here with the same sort of coefficients. One of them is 1 minus 2gm over rc squared, and the other one is 1 minus 2gm over rc squared to the negative 1. So that's all in the denominator. Now, r over here stands for radius. So we have a radius of 2gmc squared. What we're getting is 1 minus 1. And obviously, that equals 0. And for the coefficient of dr squared, that means we're getting 1 over 0. On the other one, for the coefficient of c squared dt squared, we're getting 0. So at that radius, which we call the Schwarzschild radius, we get an event horizon. Now this is the trick. If you extend the solution mathematically past the event horizon, instead of stopping at the singularity and saying you can't see anything past it, you find it describes two connected universes. That connection is what we call the Einstein-Rosen bridge, and it was discovered by Ludwig Flamm in 1916. And a couple years later, it was rediscovered by Albert Einstein and his colleague Nathan Rosen and published. Now, what is this Einstein-Rosen bridge? This, for example, is a bridge. It connects two regions of space-time connected through what we call the throat of the bridge. In theory, you could enter one side and exit the other, and both sides are different universes. But there's a catch. The wormhole itself, the bridge, is not stable. The bridge pinches off so fast that nothing can really pass through. It's like a soap bubble collapsing before you can stick your finger in, right? It's just... Now, decades later, physicists Kip Thorne and Michael Morris asked, what would it take to build a wormhole you could actually travel through? This here is their general formula, that we call the Morris-Thorne traversable wormhole metric. The key part is this B of R, its shape function. It tells you how the wormhole throat curves, but for it to stay open, you need something weird. You need matter with negative energy density. Now, what is matter with negative energy density? The condition of negative energy density is a theoretical concept in physics where we have a region of space and we have another region of space that is a vacuum. Now, a vacuum already has the least amount of energy as possible, but if we have a region of space anywhere possible that has a lower base energy than a vacuum, then that's what we call negative energy density, and it potentially could cause space-time to curve in the opposite way to normal positive energy and space-time. Although this hasn't been observed directly or anything, people in quantum physics and in general relativity physics and string theory are really searching for it because this could solve a lot of questions and just open up a whole new world of physics as well. As a side note, this condition also means that the energy density plus the radial pressure has to be negative. And that basically means that there is exotic matter. We don't see this in normal physics, but quantum effects like the Casimir effect or something could hint that it's possible in tiny amounts, and that's all we need. So mathematically, wormholes are consistent with relativity. Physically, though, the problem is we need stuff the universe doesn't really seem to hand out in bulk or at all. The Einstein-Rosen bridge shows wormholes can exist in the equations, but they collapse instantly. And then the Morse-Thorne metric shows how to imagine a stable one, but it demands some sort of exotic negative energy density matter. Right now we're stuck between the math saying yes and reality saying, "Oh hell no! That's hell no!" But if they exist, what could wormholes mean? If they exist and are stable, that would completely rewrite how we think about distance in the universe. Right now, light from the nearest galaxy, Andromeda, takes over 2 million years to reach us, and it's literally the nearest galaxy. A wormhole, though, could connect us there instantly, turning a journey longer than humanity's entire history into a single step. And for space exploration, that's not just a game changer, that I guess literally a reality bender. Like, it makes it so much more fun.
Nice.
But wormholes go beyond just shortcuts, right? If the multiverse theory and idea is true, the notion that other universes might exist parallel to ours, wormholes could act as bridges not just across space from our galaxy to the next galaxy, but across entire universes. And that means they wouldn't just be cosmic highways, they'd be gates into like realms we can't even imagine. And then comes the possible wildest idea: time travel. In relativity, space and time are linked, right? So if you can accelerate one mouth of a wormhole close to the speed of light and bring it back, two ends could experience time differently, and that effectively creates a loop in space-time, in which in principle could let you step into the past or in the future. Whether nature actually allows that is another question, but the wormhole math doesn't rule it out, at least. Now, what are wormholes not? In Hollywood, wormholes are flashy, they're glowing tunnels, and spaceships fly through them like theme park rides, and they're very visual. Their spectacle is meant to look exciting, but real physics tells a much different story. First, wormholes don't have to look like that at all. They might not even be visible to the naked eye. From the outside, a wormhole could look like nothing more than like a black sphere, indistinguishable from a black hole. And the sci-fi tube is really just an artistic way of showing a higher dimensional concept on a movie screen. Second, obviously, like I said, stability is a huge problem. The original Einstein-Rosen bridge collapses instantly, so even traversable wormholes in theory demand exotic matter with negative energy density to keep them open. Now, we don't know how to create that on the scale needed to keep it open for a long enough period of time, and without it, wormholes are gone before anything passes through. If you even have a little bit of negative energy density, you can open a wormhole maybe, but it won't last long. And finally, wormholes aren't casual portals you can just stroll into with a spacesuit. The gravitational and tidal forces near the throat would be immense, like I said, close to a black hole. Even if we could stabilize one, stepping through would be far riskier than like the smooth, polished rides that movies suggest. So the pop culture version of wormholes is fun, but it skips over the harsh reality that nature doesn't really hand out shortcuts easily. So yeah, in conclusion, are wormholes real? Mathematically, yes. They're perfectly valid solutions to Einstein's equations. We've found possible ways for a wormhole to stay open for long enough, but physically, not really. We've never seen one in nature, and the physics needed to stabilize them may be impossible with the ingredients that our universe actually provides. But that uncertainty is what keeps scientists fascinated, right? If the universe is somewhat infinite, the possibility remains that wormholes are out there somewhere. And one day, if we find one, we won't just be confirming a piece of math. We'll be stepping into a new era of physics where the impossible suddenly becomes possible. Maybe time travel, maybe multiverse theory, we don't know. Maybe we can actually go and visit other galaxies. Anyway, thanks for watching, and keep expanding your universe, guys. And who knows, one day you might find a wormhole. See you next time.
Don't forget to like and subscribe. It's free, and you can change your mind at any point in time, and it really helps me out as well.